morning, folks. Miss J here, getting ready to take you into day 2 of your virtual lesson in section 8-2, special right triangles. So yesterday we took the time out to go over a very special triangle, which was our right isosceles triangle, or which we called a 45-45-90 triangle for obvious reasons, because those are the angle measures of a right isosceles triangle. So today we're going to get into another special case triangle, now our 30-60-90 triangle. Okay, and there is a proof that goes along with this theorem. If you are interested, it will be posted in a separate video just to kind of shorten the length of this video itself. I do hear you guys. I know that some of the videos are a little bit lengthy and you're having some downloading issues. I'm currently trying to work on that, so stay tuned. I will probably be posting via YouTube soon if I can ever figure that out, because you know Ms. J is not very tech savvy, so it'll take me a minute, but I'll definitely get there, just to ease some of your downloading issues or whatever the issue may be. But stay tuned. I'm definitely open to suggestions. A few of you have given me some pretty good suggestions, which are actually helping me. So feel free to, give me some advice or what's helping you, what's working for you, what's not working for you. I'm definitely all ears. So just keep in touch with me about that. Anyway, just to keep this shorter than usual, in a 30-60-90 triangle, the length of the hypotenuse is twice the length of the shorter leg. So, first and foremost, the hypotenuse is twice the length of the shorter leg. We also have that the length of the longer leg is the square root of 3 times the length of the shorter leg. Okay, so let's put this into a formula that you may find a little bit easier to understand. Okay, so far we have that our hypotenuse is 2 times the length of the shorter leg. Okay, we also have stated here that the longer leg, our longer leg, is radical 3 times our shorter leg. So the weird thing about this is that they put both of these formulas in terms of the shorter leg. Do you see that? So without knowing the shorter leg or having an expression for the shorter leg, you might not be able to do this, but you can, in fact, knowing at least one length of a 30-60-90 triangle, whether it be the hypotenuse, the longer leg, or the shorter leg, you will be able to find all 3 sides. Okay, whether you have to do that in 2 steps or 1 step, that's up to you. But let's put these formulas to the test. So problem 4. They give us a triangle. It is, in fact, a special case triangle, and being that it is a 30-60-90 triangle, what is the value of D in simplest radical form? So you first need to identify what is D. Is that the shorter leg? Is that the longer leg? We know that it's not the hypotenuse because the hypotenuse is always opposite your 90-degree angle. Although you have to see that D here, this is your shorter leg. You see that? And it's pretty clear that it is. And that makes this leg your longer leg. So you don't have your shorter leg here, and that's what we're trying to solve for, but we do have our longer leg. So we're going to put that to use as well. And we know, according to the theorem above, that our longer leg is equal to radical 3 times our shorter leg. Correct? But we don't have our shorter leg. We do, however, have our long leg, which is 5. Okay? Let me do that in a different color. We have our longer leg here, which is 5. So we have 5 is equal to the square root of 3 times our shorter leg, and our shorter leg here is D. okay? So here's the expression that we have so far. But we are, in fact, trying to solve for d. So here's the expression that we have. 5 is equal to d radical 3. Now, in order to isolate this variable, you're going to have to cancel out this radical 3 by division. And in order for you to do that, you have to do it on both sides. This is going to cancel out here, leaving you with d is equal to 5 divided by the square root of 3. Now, in yesterday's lesson, we learned that you are not allowed to leave that radical in the denominator. And in order to get rid of it, you have to do something called rationalize the denominator or multiply by radical 3 over 3 to get rid of it. And what is that going to do here? When you multiply across, you're going to get 5 square root of 3 over the square root of 9, which is in fact 5 radical 3 over 3, which is equal to d, or our shorter leg. Okay? So why don't you take a minute, if you'd like to, pause the video before you delve into that you try. So in this you try, it says, from problem 4, what is the value of f in simplest radical form? Now f, if we take a look at this diagram, f is the hypotenuse, okay? F is in regards to the hypotenuse. But it does make things a little bit easier because we did already find the shorter leg, which is going to help us. So we know from our theorem that our hypotenuse is equal to 2 times the shorter leg. And we already found in the previous problem that our shorter leg was 5 radical 3 over 3. So in order to find our hypotenuse here, which is f, let's do that in orange, our hypotenuse being f is equal to 2 times our shorter leg, which we found in the previous problem to be 5 radical 3 over 3, okay? Now, be careful. Follow simple algebraic math here. This is 2 over 1, okay? So you're simply multiplying across. You're going to get f is equal to 10 square root of 3 over 3, okay? That 2 does not get distributed inside the radical. You cannot do that. That is forbidden. If it's underneath the radical, leave it. Don't touch it. Only things outside of the radical can be dealt with, but you're not multiplying that 2 to the denominator either because it's 2 over 1 technically, okay? So moving into problem 5. Problem 5, apply the 30, 60, 90 triangle theorem to a real world problem. So an artisan made pendants in the shape of equilateral triangles. And this is actually where, if you're interested in seeing the proof of why the lengths of a 30, 60, 90 triangle are the way they are, it is derived from equilateral triangles. And there's an actually a pretty interesting proof on this if you're interested. I will post on a separate post. The height of each pendant is 18 millimeters. What is the length S of each side of the pendant? So let me take the minute to, let me sketch out an equilateral triangle here, okay? Because they're saying that this pendant is an equilateral triangle. And it's saying that the height of the pendant, the height of this pendant is 18 millimeters. Now, it's important to know that the height of this pendant is actually your altitude, which we did learn in a previous chapter. Your altitude, and this altitude is actually the bisector, so it bisects this into 30 degrees each. Remember, your equilateral triangles are all 60 degrees each angle, right? So it cuts this top vertex angle into 30 and 30, and it's a perpendicular bisector cutting this into 90 degrees as well. So this is actually where the proof is derived from, or where a 30, 60, 90 triangle comes from, because it is an equilateral triangle cut in half. So if you notice, each of these sides in an equilateral triangle are the same length, correct? Well, what are they looking for here? You also have to notice here that that altitude or the height cuts this into two equal congruent triangles, but we're going to focus on half of the equilateral triangle here because they gave us the height. So we know if we're focusing on this triangle, S here would be your hypotenuse of this triangle. Now focus on this little piece right here. This piece, let me back this S up a little bit. In regards to the S, if the whole thing is S and this piece is actually cut in half, then that means that the length of this piece right here is half of S. Do you agree? If the whole thing is S, then the altitude or the height cutting it in half is a half of S. But we are looking for the length of S here. So what do we have to do then? Okay, so according to our theorem, we know that our longer leg, which is actually the only thing that they're giving us, which is the 18 millimeters, the longer leg is equal to radical 3 times the shorter leg, correct? So let's plug in some pieces of information that we have here. The longer leg we've established is 18 millimeters. The shorter leg, we don't know a value for it, but in regards to S, we know that it is a half of S. Okay? It's half. That's what the value of this shorter leg is here. Here. This shorter leg is half of the entire length S. And we're trying to solve for S here. So, let's baby step this. 18 is equal to, this would be radical 3 over 2 times S, is what I have, right? If you multiply. Now, 18 is equal to, you're trying to isolate S here. You want to get S by itself. And just like, I know that the radical might be intimidating you a little bit, but don't let it. So, I'll give myself some space. Radical 3 over 2 S is what we have. And I backed that up for a reason. I moved it over for a reason because I'm trying to isolate S here. And in order to isolate S, you need to get rid of this radical 3 over 2. And in order to get rid of it, you need to multiply by the reciprocal of it in order to cancel it out. Because then this cancels, and you're just left with S on its own, which is what I'm looking for. But be careful, because if you're doing that to one side of the equation, you also have to do it to the other side of your equation. Okay, so you do wind up getting S is equal to 2 times 18 is 36 over radical 3. Again, you cannot leave this like this. You have to rationalize it. Once you do, you should get 36 radical 3 over 3, or 12 radical 3 when it's reduced down. But because we're dealing with a real world problem, it's asking to the nearest tenth of a millimeter. To the nearest tenth of a millimeter, what is this equal to? So when I put this in decimal form, I get 20.78460969, something like that. Round to the nearest 10th place, so you want to round it to this place. Okay, you should get S is approximately 20.8 millimeters. Okay, which is what I have as my solution. So take a minute to work on the U-Tri on your own. You can pause the video if you like. It says, suppose the sides of a pendant are 18 millimeters long. So now they're not saying, they're not talking about the altitude or the height anymore, the side itself. So that's referring to the hypotenuse now is 18 millimeters long. What is the height of the pendant? So they're switching it up here. What is the height of the pendant to the nearest tenth of a millimeter? Again, they're talking about an equilateral triangle. And they're saying that the side lengths are 18. 18, 18, 18, correct? They're looking for this guy, which is your height. Okay? So, I can clearly see from this image what the shorter leg is, and I'm sure that you can also, but if you like, you can do this in 2 steps, okay? So S is equal to 18, which is your hypotenuse, which is what I gathered from this, and I did sketch you a little diagram just to explain that. Okay, so we know that our hypotenuse is equal to 2 times our short leg, or you can say, because our hypotenuse is 18, it's 2 times, we'll call our short leg x, and then in order to solve here, you're going to divide by 2. So then 9 is equal to our short leg. But that's still not answering the question because they're asking for the height of the pendant, which is in fact our long leg here. So we would have to take this short leg and apply it to our longer leg formula. So I'm doing this in 2 steps. So our longer leg is equal to the square root of 3 times the short leg, right? Which means our long leg, which we designated as h, is equal to the square root of 3 times 9. Or we could simply say 9 radical 3, which is approximately, decimal value is 15.5884577, something like that. When you round to the nearest, what did it say, 10th of a millimeter, which would be this place, you're going to get approximately 15.6. Okay? Alrighty guys, that'll wrap up our lesson for today. Stay tuned. You will have homework for tonight since we've completed this lesson. You will, in fact, also have a quiz tomorrow. Stay tuned for details about that quiz up on Google Classroom. Alright guys, have a good day.